Thank you. So this is a work that is based on these three people which appeared in this work, and some more work will appear soon. But it's like let's see. So I think this audience doesn't need any introduction to this field, but let me just for completeness start with the question that I'm trying to think. So my long-term goal is to find rules for perturbative quantum field theory involving higher spin particles. Okay, that means some sort of rules within which I can also compute loops and all that. But the short-term goal is to do something much more basic, is to find out tree-level scattering amplitude involving two massless photon or graviton and two massive higher spin particles. Okay, I'll make the question precise as we go along. But important thing is that what do we mean by higher spin? So just a quick recap. So we are in the flat space. So the symmetry transformation of the flat space consists of translation, rotation, and boost. This is known as the Poincare group. And a quantum particle is by definition unitary irreducible representation of the Poincare. Okay. Now the quantum particles are uniquely determined in 3+1 dimension. It's actually determined by mass and spin. But if you are going in higher dimension, it's basically representation of SON, which means the spin consists of the eigenvalues of the Cartan generators, which means spin consists of this floor of n-2 real numbers. So spin is a single number in 3+1 dimension. In higher dimension, it's not necessarily a single number, it's some set of numbers. Okay. It's a representation, yeah. It's a irreducible representation of the SON. Yeah. So in n+1 dimension, the quantum particles can be characterized by the little group SON representation. So quantum particles correspond one-to-one correspondence with the Young tableaus. Massive particles, I'm sorry. Yes, actually even massless, but in that case I have to do SON -1. So we, in this case, in this talk, and that's related to the question you asked at the beginning, in this case we consider quantum particles which already correspond to the completely symmetric traceless Young tableaus. This is everything in 3+1, but this is only part of the story in higher dimension. And if you are coming from a string theory background, then this corresponds to the particles in the leading Regge trajectory in string theory. Okay. So in the literature, particles with spin more than 2 are usually denoted as the high spin particles. And in Weinberg, in 1960s, argued that there cannot be any interacting theory of high spin particles which are massless. So that's why whenever I'll talk about high spin, I necessarily mean it's massive, because there is no interacting theory for mass.
Can you give us like a 1-minute review of this?
So the way it fails is that the soft theorem fails. So basically the soft photon theorem works because of charge conservation. Soft graviton theorem works because of momentum conservation. If you have a soft spin 3 particle, then you need a p nu sum over them has to be 0 for the soft factor to be gauge invariant. And that is typically not conserved in a scattering process, and that's why the soft, the long range interaction goes to 0. Actually, this argument should be made precise. You can always couple it to the analog of the field strength. You cannot do the minimal coupling. You can always coupling something like the analog of Riemann for spin 3, but then that will be very, very short range. It has no long range correlation. The piece come from 1 over r is because it couples to the potential, not to the field strength, and that kind of thing will be ruled out for spin 3 and above because you cannot make it gauging way.
And would it also be true that if we just computed, let's say, for particle scattering of higher spin particles,
yes,
there will be no way to do it without violating Regge group?
For 4 point, you mean with
let's say spin 4, just to start with. Massless. Take spin 4, spin 4, spin 4, spin 4. And say you take spin 2, spin 2, spin 2, spin 2, that's Einstein gravity. We know that saturates.
Yes. So if you naively take that answer and do that, then as I told you that the minimal doesn't work because it's not gauge invariant, which means you will couple through field strength. So that will necessarily grow faster in the ultraviolet.
And it doesn't work because it was not gauge invariant.
Yes.
So maybe that's another way of, would that be another way of saying it, that any interaction that you can write down?
That is also true. Yes, that's also true. Because even the minimal coupling, if I completely ignore gauge invariance, still it grows faster than this. Okay. So,
sorry.
no, please.
Would it also be true that 2 gravitons, two spin 4 particles That's what
No, he's asking massless. Massless, I think it still does it, but I have to compute it. Yeah. Because it just the vertex has 3 derivatives or something. So as you increase spin, spin S has S minus 1 derivative. Sorry, spin S, massless spin S has S derivatives in the vertex, the minimal coupling. The non-minimal has more derivatives. So, yeah.
So this is in contrast with Einstein gravity, where the leading order for graviton scattering does not involve Riemann.
No, no,
Whatever.
yes.
So there's no way, the key point here is that there is no way to gauge invariantize the thing without involving these.
Correct. Yeah. 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 That's true for even 5/2 and above. So even for fermion, you can extend.
This is written somewhere. This is in Weinberg.
I don't think it's, I don't think it's in Weinberg's notes, but he basically stops at spin 1 and because it's Weinberg, right? So he only, I don't think he wrote it, but if you just follow the steps, it comes out that. Yeah. So in 3+1, black holes are also characterized by the same 3 quantity, mass, charge, and spin, as quantum particles. And in the recent literature, there has been some speculation, is there some connection and all that. At this point, to me, it's just a fact or a coincidence, but nevertheless, I thought of stating these things. Okay. Sorry? Coincidence is that black holes are characterized by the same 3 quantities as the quantum particles. But the Einstein equation solution, the metric is really different, right? It's not around Minkowski, right? So even the nonlinear solution is characterized by these 3 things.
You're saying the no-hair theorem.
Yes. Yeah, right. So, okay, before I go into the details, so when I say high spin particles, this will be denoted by this kind of rank S objects, rank S tensors. And they satisfy this kind of condition, which are known as Pauli-Fier's condition, which means they're transverse, they're traceless, and they're symmetric. Okay. So in 3+1 dimension, you can show that this condition implies there is 2s+1 polarizations, right? This step doesn't have any physics, it's just a shorthand notation. In order to write these quantities, I will always write this as some product of vectors, zetas, zeta mu1 dot mu s, such that this condition boils down to zeta is null and k dot zeta is 0. So which means if I have an object like this, I will write it in this way. This is just a shorthand notation. At least in my understanding, there is no physics. Symmetric. Yes. At this point, I'm only working with symmetry. No. That's what I'm saying. This is not a statement about representation or any physics. It's just a shorthand chemical potential way. Just a way. Whenever I go back to this expression, I'll take derivative with respect to zeta and write down that expression. This is not any. It's just a shorthand way.
But you don't. The important thing is you don't lose any.
You don't lose any information. Correct. Yes.
Because it has the same symmetric properties.
Correct.
Both symmetric and.
Right. Exactly. Okay, so the state of the art at this point is that the perturbative quantum field theories with massless particles, only massless particles in the sense spin 1, spin 2, spin 3/2 has been well understood. People from this audience have classified the 3-point function and also the 4-point function of 2 massless, 1 massive. 4 years ago, we took that answer and tried to see what should be the structure of the 4-point function. But that was basically the 4-point function of 4 massless particles due to a massive exchange. So the next non-trivial thing would be to do 2 massless, 2 massive, which I will call as Compton Scattering. So that will be the scope of this talk.
But the conclusion that massless high spin particles have to have trivial interactions.
Massless high spin particles
Have to have trivial interactions.
Higher spin particles will have trivial interaction, but if it has spin 1 or spin 2, then we have good theories like Young. Yeah. So when this is 2 massless, 2 massive, this results, even this work is for 2 photon and a 1 higher spin and 2 graviton and a higher spin, not exotic spin 3 or something.
And when you say structure 4 massless scattering due to massive, the thing you already did,
yeah.
Massive exchange, it's a massive exchange in a given representation.
Again, we did the symmetric representation.
It's a symmetric in the spin is.
Yes, correct. At this point, actually, this can be very easily generalized to mixed symmetric. So there is this, this method, this people, Karen Hout and Para Martinez and all these people say this weight shifting operators, using which you can easily generalize it to mixed symmetric. Yeah, so in that sense, it's not hard, but again, I don't think any explicit literature with the closed form answers are there.
Particular reason you are interested in higher spin particle, external particles?
No, and just as I told you that I'm first focusing on the 3-point function that has been understood. Now let's focus on the 4-point function, and in the 4-point function, the simplest one will be 4 massless, either contact or exchange has been understood. So the next non-trivial one, if you ask really my motivation, then the next non-trivial one is actually to understand 2 massless, 2 massive. That will be the next non-trivial scattering amplitude in this kind of theories. If you're asking some bigger motivation, I'll give something. But if you just take it as a bottom-up way to construct higher spin theories, then I also feel this is the next natural thing.
Higher spin.
Yeah, that's what I'm saying. I want to construct perturbative Feynman rules, which will be giving me good loop amplitude, good EFTs.
What about 3-point functions of the massive higher spin particles?
3 massive.
That has been calculated.
Again, Suman, is it written for any spin? Sorry? Any mixed symmetrical. Three massive is the easiest.
Go to the
Easiest.
frame.
Three massive is the easiest thing actually.
The question you can ask is any of them are not CRG viable.
That I think he has a paper.
But of course, this will be CRG violating once you do a exchange.
Yeah.
Yes. Yeah. Right.
Yeah. So in that sense, I have nothing to say.
Yes.
And he showed. Yeah, spin 2 you showed it, and I think high spin. Yeah, I think the closed form answers are there, but same method can be extended.
If if these thin particles, you get a 4-point function out of 3-point functions by mod square, because there will be a propagator, 2 of these 3-point functions and mod square. And if these things all, the 3-point functions are such that any exchange automatically violates.
Because it is
It's just like the exchange by itself is here.
any finite number of exchange will be. Yeah.
Is that the reason that you doing with the exchange of symmetric spin is easier because then you can contract with momenta?
For scalar, it's very easy. For graviton, I will not say it's very difficult, but it is not as easy as scalar.
Basically, a scalar spherical.
Yeah, and in this case, you get tensor and all this spherical harmonics. Yeah. Okay.
The last line, when you say this scattering, you mean exchange diagrams? Or
Yes, I mean exchange. I'll be doing exchange diagrams. I will not be.
contact diagrams. People are.
No, I do. Again, I don't think so, but I don't.
And in exchange, what kind of fields you are considering?
Symmetric. This talk and whatever we have done till now is only symmetric. This can be extended to mixed symmetric, but we have not done this part yet. Massive and symmetric traceless ripple. Spin 2 and all that. But I think this thing contact is not very difficult.
What I was thinking is that if exchange particle is massive,
Hmm.
then you can integrate it out and write as an effective theory.
Yes, that you can do.
So finally, all the answers will contact.
Yes, but well, when I spoke about the motivation, you will see that I want to also understand things in the regime where the mass is of the energy scale of the scattering. If that happens, what happens? Very far from there, but at least to have those expressions. Okay. Okay, so now related to the question you were asking, so this has recently some amount of interest has been generated by the fact that Compton scattering has been very useful to understand scattering of gravitational wave from car black holes or car scattering. Okay, I'll elaborate on that part. So in that sense, from phenomenological side or gravitational wave phenomenological side, there has been some interest to understand Compton amplitude, mostly in the spinor helicity language, but this is related to some observables. We'll talk more about this.
What is happening? Black hole is scattering or what?
Yes. So ideally, one would like to understand black hole scattering. So something like this. And you can compute it by cut of the compound amplitude. So basically, if you have a two massive, two massless, two massive, three massless, two massive, four massless, you can construct all this by gluing. So in that sense, compound amplitude plays a very important role in this kind of gluing picture.
So these particles are black holes and it's not.
Yeah, I will talk about the limit. It's not strictly black holes. I have to take a limit to make sense of it as a black hole. I'll elaborate on. So these expressions of electromagnetic and gravitational compound amplitude is available in the literature using the massive spinohelicity variables. But it is known that these amplitudes known to have spurious poles. This known to have poles which have no physical meaning. Okay. So this was one motivation. Second motivation could be, this audience knows this part very well, that high derivative corrections probably is coming with higher spins. And as you know, in that paper, they took the string theory answer and they showed that it is good with causality. But is it really possible to make some more thing that if there is a massive exchange, can I compute the time delay and do an infinite sum and make sense of it? In order to do that, I need to have the amplitude. Right? So in order to, at least in my mind, in order to need this completely understanding, all the things that has been discussed till now has to be completely spelled out, and then one can maybe do some sort of bootstrap or something. That could be one motivation to compute this kind of amplitudes.
Yeah. In general, in this program of trying to show uniqueness of Virasoro-Shapiro amplitude,
Yes.
to have all these explicit forms will
Very useful. Yeah.
presumably.
Yeah. Okay. So this is the thing, another thing I was saying, the gravitational wave spectroscopy. So for example, people are interested in gravitational wave from black hole scattering, black hole in spiral, merger, neutron star scattering. And it turns out to be hard using GR, but people have done some Feynman diagram technique. So let's try to understand what is the idea. The idea is basically multiple moments. So if you look at a black hole from far away, then a black hole can be approximated just with the multiple moments. For example, a spinning car black hole, far away, the car black hole can be approximated as a point particle with spin. So I'm basically doing multiple expansion. And then what you do to get from this to this is this thing. So then we take a quantum particle of spin s. So here s is a dimensionless integer. Then we take s goes to infinity, h bar goes to 0, keeping the dimensionful h bar s fixed. So this h bar s will be the classical angular momentum for the rotation of the classical body around this axis. So that will be that's basically the thing they do. They compute this and then take this limit. And they say this is related to the classical scattering of black holes. Okay. No, so they actually are interested, strictly speaking, in the infinite spin limit because they're only taking classical limit. It's like particle in a box you are trying to do using quantum mechanics. It'll go to large quantum number and all this. You will take this limit in this way. You will take s goes to infinity, h bar goes to 0, keeping this fixed. Sorry?
At which moment can we approximate this black hole as a particle?
As I'm saying, it is basically, okay, strictly speaking, we are in a length scale which is far larger than the length scale of the black hole, which is the Schwarzschild radius. So the observable we are doing, if the Schwarzschild radius is Rs, then Rs over R is much, much less than 1. Then you can do this. So the merger phase cannot be understood in this way. It's only the...
And it's not the 2 1 scattering.
No. So we are interested in this.
Yeah.
But Shuman's point, I think, was that Kerr black holes have this extremality bound.
Yeah.
You have to be
infinity bounded.
If the S is large, mass will also be.
Yeah.
Mass has to be, oh, I'm sorry. Yes, you are right. Actually, when you take this limit, we also take mass goes to infinity, but S over M, the angular parameter finder. Okay. So the point is that then people are saying that this black hole scattering can be approximated as classical limit of some high spin scattering. Okay. The only information then you have to put is that what is the 3-point function of the black hole? What is the structure of the 3-point function? That's an open question. We'll come back to that question. But question is that once you understand the 3-point function, then black hole scattering can be understood using this way by taking some sort of a classical.
And you want 3-point or higher spin, and spin.
Correct. Or spin 1. I will restrict myself to spin 1. Yeah. Sorry.
But Presumably in this scattering process, all the ladder diagrams will come.
Yes, correct.
Iconized.
Correct. Yes. Some sort of a ladder diagram, and in that the first non-trivial contribution comes from this. This is completely understood for Schwarzschild because it's a scalar coupled to graviton. The difficulty is car coupled to graviton because we do not have a higher spin QFT.
Oh, what do you mean by it's understood for Schwarzschild?
So Schwarzschild people have managed to show that various things, for example, the scattering angle deflection, that this is called this PM expansion, post-Minkowskian expansion. People have managed to derive those things by doing an order by order computation by scalar coupled to graviton. Analog of scalar QED, but with graviton. So that has been understood. Large, I think up to 5 loops or something. Spin is the problem.
And how as at higher and higher orders, you will see more and more of the black hole.
Correct, correct. You will
What
see.
do you say only past and
You will see more and more multiples of moments of
multiples. Multiples of
black holes, and so you will get orbital angular momentum, spin angular momentum type of interactions, orbital angular momentum interaction. All these things starts coming. So
No, but sir, where is that model in this picture?
in this picture, first you take the scattering amplitude, first you compute it. Then you take this classical limit. And then there is some well-defined prescription. I have not put it in the slide that how to take the Compton amplitude and map it to a classical observable. That people have derived. But once you have this, they have a straightforward and then you get this.
What do you mean when you say that higher and higher orders in what?
So in this business, what people are trying to do, they're actually trying to find a classical Hamiltonian of the two black holes. In the far away, they want to understand black hole scattering as some Hamiltonian evolution with some Hamiltonian terms. So the first term is free particle, then some GM by R, then some spin-spin interaction, then some multiple interaction. So they want to find those terms of the potential using this scattering and some sort of a Born approximation.
in size of black hole divided by this.
That's the expansion parameter.
When they're really nearby, the thinking of them is just particles.
Doesn't.
It is going to infinity.
Response to what kind of approximation?
I would imagine those.
Yeah.
I would imagine the 3-point functions would become more and more.
Yeah.
Because you just have like minimal coupling with the mass. Then there would be like a curvature times times particle count. You know, like a B dot S.
No, but they're finding it anyway.
No, I think
But when you take this S goes to infinity, it will be all the multiples are there. If we strictly do that S goes to infinity, I have all the information. But we'll always truncate at fine.
S goes to infinity because then the black hole can have arbitrary weakly shape.
Correct.
Yeah, so all the various shapes of the black hole. Why is that there? Well, why isn't that there?
No, that doesn't have hair. They are all determined by the no-hair theorem. But it's just the form of those multipoles are very, very precise. So to put it differently, finally, when these gravitational wave detectors become more powerful, they want to understand the same thing for neutron star, where these multipoles are no more dictated by no-hair theorem. So you will do the same business in that case. But in case of black hole, all the multipoles are there in a closed form, but they are dictated by 3 parameters for no-hair theorem.
Yeah, it's particular.
Yeah, but in general, one would like to understand for neutron stars also.
What since these 3-point structures are more and more suppressed by
You will see, I will write down the structures and then we can.
black hole, this thing.
Yeah, let me write down the 3-point functions and then we'll talk about the 3-point function. Okay.
This S goes to infinity, n goes to infinity also.
Yes.
And the radius directly depends on n.
No, as I said, as I understand this part,
The radius of that black hole itself.
radius, you are saying the Schwarzschild, I mean, the Schwarzschild radius goes to. So in this way, the observable you compute is insensitive to that.
So your difference is much larger than this.
This is a 1/m suppressed or something.
It's infinity h bar times n, which will determine the radius as well.
Oh, yeah.
Which is the Compton radius or something. So then this is possible to do from this thing. And another thing could be just to understand the loop corrections. This is something Loga is deeply interested. If I couple it to standard model, what kind of changes happen to the standard model beta function and all that. So we need these things for various reasons. That's a broad motivation. So as you know, the key difficulties in this business of higher spin for exchange amplitude is the propagator is hugely complicated. I mean, I'm sure many of the people worked in with this, and it's just mess. I mean, and if
For black hole purpose, we just need spin 2, right? Spin 2
no, 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 spin 2 will be the graviton, but
Ah.
I also need the higher spin propagator.
So you are not necessarily interested just in this leading order Born.
No, 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 no. People want to understand more and more precise information about the potential. Leading order is, I think, just Newtonian.
But why can't we just use cyclized expression then?
But in order to do the iconized expression, you need the scattering amplitude. You need the closed form expression, and then you will do the icon.
So if you just need the 3-point function, and then there's some standard exponential formula. Or maybe starting with the Born approximation, there's some.
Again, I forgot now the details, but when I did it, what I understood is that just the 3-point function is not enough. The 4-point function plays a role in that. The exchange diagram.
You mean exchange for
Exchange 4-point is important to compute this. I can look at this and I can come back to you. I don't remember. So this propagator is a mess, and this propagator is this expression where we have theta, which is this form. It is symmetric, traceless, transverse, all these things. These coefficients are uniquely determined by that.
Does very matter. I mean, the exchange 4-point, what that will do is somehow take into account the fact that the intermediate particle is not exactly the same moment. Right, in this iconized, you ignore the effect of momentum transfer. I suppose the new information here is that
Momentum transfer, yeah. Because you want to compute the impact. No, one thing people want to compute is impact factor, for example. Impact factor is Fourier transform of the momentum transfer. Another is scattering angle. That also somehow depends on this. That if you throw 2 star black holes, what will be the scattering angle?
Suppose you have 2 particles, 2 black holes going around. They are changing trajectory. So as they come nearer and nearer, the change in trajectory will come
only some limit
where they're very far away. So I would imagine that in this expansion, you also have to systematically go away from economics. Because you have to take into account
Change in that.
Not quite clear what sort of diagrams.
People have shown that only this kind of ladder diagrams, but not just 3-point, the full ladder diagram contributes.
No, I mean, when I say iconal, I did mean these types of things.
But iconal, you do a sum.
Approximation is not to be used.
You do a sum. Here you don't do a sum, you take it order by order. For example, the tree level gives you the first order correction to the potential. I mean, correction to the free theory. This one gives you the second correction, which is known as a post-Minkowski correction. So higher and higher loops in this case corresponds to higher and higher order post-Minkowski correction to the potentials. Okay. So this is the main difficulty in this business. Okay, and that's yeah, it's not easy. So we'll come back to this. So let's now talk about the 3-point function that we are discussing. And this is basically the physics is it is basically multiple moments of high spin particles. So if you look at the 3-point function of 2 high spin particles of spin s and 1 massless particle, then it has 2s plus 1 structure in 3 plus 1 dimension. Okay, in 3 plus 1 dimension, there are 2s plus 1 structure. There are 2 series. It may look complicated, but for example, if you try to have a physical understanding, you take this term and put n equal to 0. Then this is the Coulomb interaction between the high spin particles.
The one massless particle, does it matter what spin happens?
So depending on that, you will either have this or it's square. I mean, I'll use some sort of a double copy or
The
something.
number of structures.
I kind of feel that 3 plus, okay, thank you. 3 plus 1, the number of structure is always 2 plus 1. Higher dimension, graviton has more structures. And in my understanding, that is not still been completely classified.
In 3 plus 1, all massless particles behave.
Yeah. It's 2 helix,
Two polarized.
2 helix, yeah, that's it. Okay, so in this is a complete kind of, okay, I think we managed to show this, that if you are above 4 and above, then these are all the structure of a photon. So photon doesn't go beyond this, but graviton has more structures as I go beyond 3 plus 1 dimension. But what are those, how to classify, what is the counting, it's still not cleaned up yet. At least not by us. So this is the Coulomb interaction.
Confirmed field theory, right?
Sorry.
There are papers written from the confirmed field theory. So it's where they write down these structures and then they have some, so they classify these.
High spin current, and stress tensor and stress.
General type of 3-point functions.
Okay. Okay. I
I
tell.
thought they did that.
Okay.
Then Simon's Ruffin is also one of the models.
Check it. I don't know this. So this is the first term, which is the Coulomb interaction, which is responsible for the soft theorem. Here the first term is the magnetic moment, the thing that the coefficient is called anomalous magnetic moment and all that. So this is that 3-point function. So in general, there are 2s plus 1 different structures, right? Which means that the space of 3-point functions of photon coupling to higher spin is 2s plus 1 dimensional. Okay. Now the questions you can ask is the following: that in the 2s plus 1 dimension, yes, you see these are like as n increases, derivative increases. Okay. So now the question is that if I want to model black hole in this 2s plus 1 dimensional space, what point in that space I have to choose? Black hole 3-point function is some particular linear combination of all this. If I have a neutron star, what is the particular 3-point function I have to choose? Right. So if I want to take the classical limit, I have to somehow take a particular linear combination, not just moving in the whole space. But as you understand, if it's 2s plus 1 different 3-point function, then the number of 4-point function is huge. I mean, the symmetric this thing. So what we did, and that in a sense is most crucial in the following sense, we only looked at the Coulombic interaction. Why it is more crucial? Because basically it has some contact time ambiguity. I'll be more precise about that what do I mean by that statement. Other 3-point functions do not have that problem. I'll be more precise. Just give me 5 minutes. Okay. So now related to what Siraj was also hinting towards, that if other 3-point functions are okay, so other 3-point functions are higher moments of the elementary particles. So that if I take it black hole, then this will be quadrupole, octupole. Those will be related to the coefficient of the 3-point functions. Now, if you look at literature, there is some question people ask that what is the natural magnetic moment for elementary particles? And after discovery of electron, people thought it is 1 over s. So it's 2 for fermion and then it's 1 over s. Weinberg argued from some non-perturbative stuff that it has to be 2, at least the tree level value has to be 2. Okay. I don't think this question is completely settled. So the question is there any natural value of the moments of the value? Sorry, this is wrong. Value of the higher moments. People have computed in string theory, and if they do this symmetric traceless representation, it turns out to be 2. So there should be very good reason to believe probably this is true. As I said you, in this work, I will not talk about any of this. I'll only restrict to the Coulombic interaction, which is the leading interaction in the long distance. Why this is the first one here. So n is equal to 0 in the second one. So n is equal to 1 here will be the quadrupole. N is equal to 1 here will be the octupole. So
how to interpret these structures as some particular moment?
By again taking the classical limits. So I don't remember. Okay. So the way I remember it is basically the following. So that these higher moments are some classical, so let's say L. So these higher moments are some linear combination of L's, the angular momentum, right? The first moment is L power 0. The magnetic moment is like L nu, proportional to the angular momentum. The quadrupole moment is the symmetric traceless combination of L mu, L u, the classical angular momentum. So what you do is that first write this expression in terms of writing down a classical operator, quantum operator L, whose expectation value will give you the classical angular.
So K3 are the number of K3.
A3
counts K3. K1 plus K3. That counts the L. Effectively, like polynomial in K3.
Yes and no. You can think that these are the electric moments and these are the magnetic moments. And in that they count the derivatives. But you see these two have same number of derivatives. The n is equal to 0 here, n equal to 0 has same derivative. Right? Only difference is that this has their momentum. Not just that, this has the momentum of the hard particle, this has the momentum of the soft particle. So which means when you take a soft limit, then this is more dominant than the other. But if you're just on computing derivative, then these two are in the same order.
This magnetic moment is coming from the dipole term.
Yes.
Is it like you have some charged particles, they are rotating, then
That will be the classical analog. But quantum mechanically speaking, you take the dipole operator, you take its expectation value, and you interpret it as the classical dipole. So you write down the Hamiltonian, and that is the dipole coupling to the magnetic field, and you call it just the classical dipole. Okay.
sorry, what is the dipole?
Dipole operator, I think related to this, it's a total angular momentum, which is the spin piece plus the orbital piece. Okay. I can show you the literature. I have not somehow written that. Okay, now there comes the important piece, that what is the 3-point function of the black holes. And in this part, these three people, Arkani, Hamed, Wang and Wang, postulated that the 3-point function is of this form. Okay, so it's a very particular linear combination of the 2s plus 1 3-point functions. Okay, so for spin 1, this combination reduces to the Yang-Mills structure. And for higher spin, this is some particular linear combination, but that's basically the statement that the black hole 3-point function is this. Which means if one wants to understand the black hole scattering, then one should do the computation with this 3-point function. Yes.
Given the spin, it's
In this way, yes. Yes. Yeah.
take the spins and then compile it to.
You compute the scattering, you expand it in this classical limit, and that will give you the terms in the Hamiltonian. Let's ask the following question, that how do you know how classical electron will behave in presence of a magnetic field if you are starting from quantum field theory? You can compute the scattering amplitude and then take some sort of a bond and do the classical Hamiltonian. Same thing you will do, but for higher and higher moments. I'm still not computing, that should be the purpose, yes. So firstly, one should compute the most general 3-point function, and secondly, one should be doing the graviton. S is spin. S is the spin of the higher spin. 1 is the spin of the massless. Okay. S and photon. So this is the conjecture in the literature, that this is the 3-point function that you should be using if you want to do black hole scattering. So this part you heard it. Yeah. So now the question is that what is the 3-point function that one should be using for black holes? Right? And these three people conjectured that the 3-point function is of this particular form.
Is this somehow minimal?
No, okay, thank you. So what do you mean by minimal? There are two sets of minimal people use. One is minimal in the sense of the minimal coupling of, we do it in the quantum field theory way. Like drip.
The one that dominates a lot.
No, this is not that.
So then why should you read it?
So, okay, I don't think these people are very explicit about it, but the lore is basically the fact. Okay, so firstly, let's go to the spin 1. So if this is like the 3-point function of WW with photon. And WW 3-point function, as you know, has a Yang-Mills structure. Right? So what these people are saying, that is for spin S, the structure is the Yang-Mills structure times this quantity. And in case you are confused about this quantity can be actually thought in a very interesting way. So, okay, this is all blah. Okay. So in the sense that this is not precise, I do not know how to make it precise. This is just an observation. So let's take these things as coming from some sort of a spontaneously symmetry broken theory. I don't know what that phrase means. And then I can construct the field strengths, right? So what will be the field strengths? Let me call it Z. So field strength will be K mu, zeta nu, and antisymmetric, right? K mu, zeta nu, right? That will be analog of the field strengths. Now, if you have a spin S thing, you basically take this. So let's say this is mu. So the field strength of that will be basically mu1, mu2, mu s. Okay, you can check this gives the field strength for, this gives the Riemann for spin 2. Okay, this 3-point function is basically taking this for particle 1, taking this for particle 2, and taking the dot product. So this is analog of that the higher spin particles are just only coupling through some sort of a field strength, not otherwise. This statement is purely kinematical statement. I do not have a conceptual answer. Sorry? Yes. So this piece, you see this piece. This is basically product of two field strengths. This is a very particular linear combination. Okay. Now I tell you the load that is in the literature, but I don't think there is any proof. And one should do this computation to do the proof. The load is that if you use this 3-point function, then it has the best ultraviolet behavior. Correct. Which means one should be really doing the 2s plus 1, all the general 3-point function, and show that in this space of coupling constant, this space is the best. That computation is still missing.
How are you just to do this calculation classic?
This one, what do you mean?
Meaning you're interested in a black hole. So I take a per black hole coming in, I take a per black hole going out, and small exchange for graviton. Let's say graviton. Well, it doesn't sound terribly hard to me.
3-point function part, you are right, that it will basically be some sort of a multiple expansion, whether you have to do the stress tensor multiple expansion coupling to the graviton.
But there was some ambiguity about what the coupling.
The linear combination that comes out. Yeah. So in order to really take it to the black hole, I have to take some sort of a classical limit.
So, but even classically, is there still an ambiguity even with the classical limit? I mean, basically you take a classical limit, but you need to know what linear combination you're taking a classical limit of.
I think that the problem, okay, this part I don't know very well. So I think the problem in this classical limit is that when they try to compute an observable, the observable is always related to the 4-point function. So nobody has computed the 4-point function, which is physical from this 3-point function.
But sorry, there
No.
was still the question of which 3-point function.
Yeah.
The way you presented it, there were many possibilities. You chose one.
Yes.
If there was some, expansion in derivatives that justified it, some long distance expansion, it would be sort of. You're saying it's not that. So then it's not. Then I feel unclear. There's some words, but I feel unclear.
No. This part, I mean, I'm not. I also don't understand this part.
Yeah, but I was wondering if you were going to actually apply it to black holes.
Yes.
There's no mystery about how black holes come.
Correct. So that mystery, in my mind, will be settled that I compute the car black hole's angle from GR. That is also this 3-point function because it's black hole graviton.
Sorry, why do we get graviton out of?
Because it's accelerating, so it will be radiating.
A single car black hole is moving.
Oh, then it will not. Then what you would be doing is that you take a car black hole, couple it to a background metric, and do a multiple expansion of the metric and linearized fluctuation of the background and compute these quantities.
So man itself built to do some membrane. Yeah.
Membrane, sorry.
Actually, in largely black holes are membrane. Really becomes an object.
So I will not be talking about it. This is not what I will be focusing on, but this is just exist in the literature and I'm slightly confused about their role. So I thought of mentioning just for some discussion. So, okay. So we will be doing the Compton scattering. We'll restrict ourselves to the photon. Graviton amplitudes are we have done it, but we'll restrict because the philosophy is same. And we will do it only for the 3-point function when this is the Coulomb interaction. I'll try to justify it more at the end. The first justification is this is the simplest thing to do. Second justification is more involved. I'll come to that. So this is the tree level contribution. So if you want to compute this contribution from the exchange diagram, there are two contributions. It's a bit tedious, but it is doable. But if you add the two contributions, let's say this is a T channel contribution, this is U channel contribution, and you ask whether the scattering amplitude is gauge invariant or not, it turns out it is not gauge invariant. Which means if I put a longitudinal polarization for the photon, the scattering amplitude does not vanish. More importantly, it is non-local. Okay, this is just one can take that propagator, do it for spin 2, just for simplicity because it's easy and explicit.
You're missing the phi squared, a squared.
Not just that, you will see more. That's one part of the story. Because if it's just phi square a square, then it cannot be non-local. So if it was just local, that conclusion is enough. Okay. So, okay. So I'm computing Compton scattering, where this is the Coulomb 3-point function, the most relevant in the IR 3-point function. There are two diagrams, MT and MU. I compute them explicitly. I add them and I put a pure gauge polarization for them. And I ask, is it gauge invariant or not? It is not gauge invariant. And as you can, it's non-zero and it is non-local. So what Siraj was saying is that if it was local, then it's a complete story. I mean, hopefully a complete story by adding some contact term, which will be our actually conclusion, but we'll see in a... then I can probably add a contact interaction to cancel that term, but it is non-local. Sorry? 4-point exchange. This is exchange 4-point.
I mean, it's usually the case that exchange, let's say gravitons, that will be non-low, will not be gauge invariant unless you also include the usually the correct content.
Yeah. I mean, at this point, yeah, let's see. So this is some explicit answers, but it turns out to be not this. So let's see what. Massive. It's scalar QED Compton amplitude. Whether
that's what you are doing. But Shiraz said, in order to compensate it with the gain, because there is a propagator with the failure depends on the mass.
So that you will see the creator. So propagator is the discussion. Now the discussion will turn to the propagator. So how to restore gauge invariance? Okay. So here we go back to our thing which we understand very well, that we take the theory of charged massive spin 1 particle, the W boson propagator in the Arxiv gauge takes this form, right? And you know very well how it happens in this case. So one is that firstly there is a unphysical would-be Goldstone boson, which is extremely important to restore unitarity for Higgs mechanism. Without it, you cannot make Higgs mechanism work, if you are coming from scattering amplitude perspective. Okay. The would-be Goldstone boson do not decouple unless you take xi equal to infinity. Fine. This is just a resemblance that our situation resemblance xi equal to 0 because you see the theta term we wrote is precisely the theta term if I put xi equal to 0. This theta. Okay. Yes, but if you come from a BRST way, the would-be Goldstone boson is still there in the Feynman rules. It's not part of cohomology, but in order to loop, you have to take it's like the BC ghost and all this. You have to add all of them to get unitary answer. On shell, you are right, but we are doing some computation where the intermediate leg is off shell. So we need to keep things which are off shell degrees of freedom. And there the would-be Goldstone boson, if you do take the WW scattering, then just adding a contact term is not enough. You have to add the contribution of would-be Goldstone boson.
Back to this question. Being very stupid. There's you're scattering this massive spin S with a photon and then going through. Now the on-shell scattering of you're using a 3-point function for this, but for the interaction between the two. you know the 3-point function is on shell and you're using some off shell,
I'm just taking it,
extension of-
I'm just taking it and using it off shell.
some particular off shell extension, right? Because off shell extensions are not.
You are right. So I'm taking the off shell extension, which is good with spin statistics and symmetries. So for example, some 1-2 symmetry and all that. I'm using that off shell extension.
But I can always add some k squared minus n
You are
squared
right.
and something else.
You are right.
So there's some ambiguity.
That ambiguity is there, and you will see that resolution we will be proposing can be changed. I mean, if you are using a different frame than I am, the whole computation will go through. The final answer will agree, but the intermediate state will disagree.
Excellent. Now, the on-shell 3-point function was gauge invariant.
Yes.
So now I'm trying to understand. So if I look at the non-local part, that's the part where this this thing is going on.
Correct.
So it's surprising that the non-local part is not gauge invariant, because I would have thought that any non-gauge invariance would then go away when you set k squared equals m squared.
Yes, but we expect the scattering amplitude not only to be when the external particles are on shell, not only when the internal particle is on shell, but when the internal particle is off shell, but external particle is on shell, we expect it to be gauge invariant.
Yeah, but let me ask you. There is a 3-point function that you put. When the 3-point function, when all particles go on shell, it was gauge.
Correct. Yes.
Now, presumably the lack of gauge invariance is because when you extend it so that the external particle was off shell, it is the 3-point function is no longer gauge.
Correct.
Okay. However, the non-local part,
the
pole part, comes from going near to on shell.
Correct.
So, like contact of ambiguity. Exactly. I would have expected that the lack of gauge invariance would be just a contact.
So let's take this concrete example. No, this is let's take this stick and let's take the tooth Feynman gauge for Higgs mechanism. Then it's not just a contact. I mean, you really have to also add an exchange. You actually have to add this would-be-Goldstone-Boson exchange so that it satisfies the Katkowski cutting rules.
And what? Tell me again this example. What was it, please?
So I am taking, let's say, let's for simplicity take SO3 gauge theory coupled to Higgs, which is in the fundamental representation of SO3. So then I have 2 Goldstone components and 1 Higgs components. Potential is the Mexican hat potential. So when I go to the vacuum, the true vacuum, then I will have 2 W bosons, plus and minus, and I will have a photon. So that will give some 3-point function of the W's coupled to the photons coming from the UV.
Yes.
Now you compute that, you quantize the theory in the Arxiv gauge, you compute the scattering amplitude, and you do the same thing where all of these are coming from Lagrangians.
Yes.
Then just adding the contact term will not make the WW photon scattering gauge invariant. You also have to add this thing which comes from the Lagrangian approach, which is known as the would-be-Goldstone bosons to restore unitarity. So this would-be-Goldstone bosons are, so let's say if I set the gauge coupling to 0, so there are Goldstone bosons.
Yes.
Right? So when I gauge fix it, these Goldstone bosons get a mass which is dependent on the gauge parameter.
Well, but there are no Goldstone bosons there.
Correct. Off shell there are. These are not physical particles. These are not part of cohomology. But there are the Feynman rules which says that these phi's interact with the W's in a particular.
Phi was what? Phi was.
The Goldstone boson.
It's not. We can't just work with all the physical particles.
No, that will be like, thank you. So that will be like taking xi equal to infinity gauge, which is known as a unitary gauge. If you take the unitary gauge, tree level works fine because the would-be-Goldstone boson becomes infinitely massive. But loop doesn't work because renormalizability we cannot prove.
Right.
Okay. So our situation resemblance.
Basically get rid of the longitudinal polarization of the
Yes,
spectrum.
yes. This extra degrees of freedom does that job off shell. Okay.
This particle was not a massive particle to begin with.
It's a mass. Well, yeah, it's how you look at it. It's never a physical particle to begin with because, as Siraj said, there is no Goldstone boson. It's not part of cohomology.
With just standalone massive spin 1 particle, we should be able to solve.
No. At least tree level, you can make it work, not loops.
If we were doing tree level, you are right now doing tree level.
If I do tree level, then that will be not resembling xi equal to 0. That will be resembling xi equal to infinity, where these Goldstone bosons are infinitely massive.
Abhijit saying that your propagator is allowing
Option.
unphysical modes, even of the W bosons to propagate.
Correct. Absolutely.
If you just ensure the propagator was one that only allowed physical,
Sure.
then you wouldn't have.
Correct. Absolutely correct. And this propagator does not do that. The propagator we demanded, and it, I mean, I also used it in many places. This propagator does not do that job. In particular, you can take it for spin 1 and you can see it does not do the job because it is like xi equal to 0, which does not do the job. No, at this point, it's like I know it from Higgs mechanism. Why don't I try to do it in case of higher spin because I don't have a Lagrangian? I'm not providing you a derivation. At this point, I'm just saying I know this from a theory which has a Lagrangian description and this happens. Can I resemble something like that in presence of higher spin and can I make it work? I'm not giving a Lagrangian description yet. I don't have a Lagrangian derivation yet. Okay. Fine. So then this is the main conflict.
It's a shortcut would have done without the C and without the V and
No. What I'm saying is that first we were doing all on shell, higher spin, all these things. It was not working. It was non-local and non-zero. So then I said, okay, one particular point I already know very well where I have a Lagrangian, which is the W bosons, which is spin equal to 1. What W boson mechanism tells me for spin equal to 1? Why I cannot make it work? If I'm that ambitious to work for all spin, I should first make spin 1 work. And when I look at that part, I see that this is not enough. If I had xi equal to 0, I have to add this would-be-Goldstone bosons, or I have to take something analog of xi equal to infinity, where the would-be-Goldstone bosons decouple. Just this thing as it stands doesn't work, even for W boson, where we have a good theory.
And as you say, it's because the propagator is not projecting out the
Correct.
unphysical ones.
Correct. The propagator is not good off shell. The poles, actually, it has unphysical poles. So the question then naturally follows that is there a Arxiv gauge for high spin propagators? I don't know what, I mean, don't think I'm giving a Lagrangian description. It's at this point just taking the motivation from spin 1. And can you restore unitarity by adding extra particles? Because that's what spin 1 seemed to suggest.
bothering because you're talking about massive height.
No. This is gauge invariance of the massless particles. And this Arxiv is only at the level of resemblance of this propagator expression. That's what I'm saying for higher spin.
Taking it by Higgsing.
I'm taking the motivation from Higgs mechanism and mimicking it. I'm not providing a Lagrangian. I'm not giving a derivation. I do not have all those. It just, I know this works for spin 1. Let me just be blind and do it, see it works or not. Okay. Okay, so that's basically the upshot of the paper, and if we derive it, we'll be very happy. This derivation we still don't have, but point is that we take this and naively just deform it in this. We add a xi parameter by hand. Okay. And that says that this cannot be the complete prescription, it must need some tweaking, and the reason is the following. So we find that it is possible to restore gauge invariances only for two values, xi equal to 1 and xi equal to infinity. In particular, xi equal to 0, which was our original problem, does not work. And just we know from xi equal to infinity for spin 1, in this case, as Siraj was saying also, that just adding contact term is enough to restore gauge invariance.
Also in the
With C? Yes, p square plus cm square, correct. That sends the mass to 0 when you say C to 0, and that doesn't work. That's what I'm saying. It only works for C equal to infinity. And actually, you can give a derivation of C equal to infinity propagator using on-shell methods. There is a derivation of the C equal to infinity propagators.
That must just be the propagator that projects out everything.
Absolutely, on-shell. On-shell. So question is that it's related to the question you are asking what off-shell deformation you are taking. So this, if I take this off-shell deformation.
Off-shell, you introduce new propagating degrees of freedom whose coupling to the photon was not gauge.
Correct.
Nice.
Absolutely. Okay. Now it connects to the question you may have in mind why you are looking at Coulomb. This feature is only there for Coulomb. It's not there for all other 3-point functions. All other 3-point functions, you can write it in terms of the linearized field strength, which means it's also off-shell gauge.
That's no problem.
Only problem is this term. If we can resolve this term, we can resolve it for all 3 point functions. Okay. At c equal to infinity, we can find a local contact time to restore the gauge invariance for any spin. We can give a closed form expression, it works. Okay, this is some complicated thing, it just works. Interesting part for me is this one, even though I don't have a derivation. So it's equal to 1. We can restore gauge invariances, but it doesn't satisfy the cutting rules. What do I mean by cutting rules? That in the 3-point function, only the on-shell degrees of freedom will exist. What you can show is that apart from a contact term, we need particles from spin s-1 to 0 to restore unitarity. So at c equal to 1, I need a tower. I need a tower of unphysical particles, which will be important to restore unitarity. Finite tower, 0 to s-1. This is unitarity, not CRG, not UV growth. Okay. They come with a very precise 3-point function, and if you restrict yourself to W boson, it of course works.
And this is because you can add some, you've got some indices, you can contract them in pairs.
Correct. And then it gives
These
the
are
lowest.
the new off-shell degrees of freedom. That
Absolutely. Absolutely, yes. In string theory, if you look at this Siegel gauge, which is analog of C equal to 1, where all the physical and unphysical particle come in the same mass, they have the same feature. Again, it's just an observation statement. I'm not making any more statement beyond this. So the natural question is that are these the would-be Gaussian bosons? Is there a Higgs mechanism for massive high spin particles? Okay.
Slightly broken.
Is it correct for flat space? I'm not sure actually.
Yes. Energy.
Okay, so this is the open question. Yeah. So what we did is that this will be the obvious question one can ask if you're trying to.
So Siegel gauge is something in string field theory?
Yes. So we compute the Higgs theory, and we know that if you do from Higgs mechanism, it comes from all. It can show it works for all xi, not just I equal to 1 and infinity. Okay. So just because I equal to 1 works probably means we are still missing something. Second thing is that if you have done this Higgs mechanism computation, you may know that xi equal to infinity is very good for tree level, but it is not possible to show that Higgs Young-Mills is renormalizable. There is still no proof of proving unitarity of proving renormalizability of Young-Mills at z equal to infinity. People can take it finite z and prove it. Just restricting to z equal to infinity always, the proof is still not there. Which means if one would like to understand any kind of loop correction, even though this is a beautiful point, it will not be good. I need something analog of this. I need some finite c. Second question you may ask at this point is that, as you again know from spontaneous Higgs mechanism, that in Higgs mechanism, in case of WW photon, I cannot pick and choose 3-point functions. The frequent function is coming from Young-Mills theory. I have to take the full 3-point function to show Xi independence. For any other 3-point function, I cannot prove. In this case, in absence of Lagrangian, I ad hocly chose one particular 3-point function and I did the computation. Maybe adding all the 3-point function and trying in this whole space, at some point it may work and it may be related to that. Computations are waiting. Take WW photon. WW photon 3-point function is not the Coulomb interaction. It's the Coulomb interaction with the magnetic moment, where the value of the anomalous magnetic moment is 2. And for that theory from Higgs mechanism, we could show that it is C independent. If you just take this and just throw away those things and do something else, you cannot show C independence. Right? We are coming from an on-shell way, and we are only choosing a particular 3-point function. Who said there is a Higgs mechanism like thing for that particular 3-point function? Better is to compute it for all 3-point function, look at this moduli space, and see is there a special point or is some special behavior happens. That is just a computational challenge, but that we still have not done. 3-point function has nothing to do with c equal to infinity or it's a propagator. Okay. Ideally speaking, your point is related to the fact does your contact term depend on c or not, which is a 4-point contact term, not 3-point contact. Okay, it remains that thing, we could not do it. We could check it for gluons, it works. We could check it for graviton, again it works. As I said, in the black hole literature, there is this huge result on spin-helicity formalism, and I kind of feel people are missing this point. They're using a propagator which is probably they should not be using. If you use this formalism, it works for the spin-helicity formalism. Okay, but this is only an observation. It is not a precise answer. So first question will be to prove that is it possible to show Goldstone-boson equivalence theorem for high speeds. This statement is that if you compute WW scattering and if you go to very, very high energy and you took the longitudinal polarization of W bosons, you can show that that scattering amplitude is same as if you are doing the scattering amplitude with the Goldstone bosons. That's a feature that is coming from a Higgs mechanism. Can you show it for arbitrary spins? Second point is this space of 3-point function. Is there a special point where the UB behavior becomes better? For that, we need this whole 2s plus 1-dimensional answer and then check, is there a special point where something special happens? Maybe that will help. I don't know. Finally, one would like to compute the graviton and take the classical limit for gravitational wave physics. But the part that is really I'm interested at this point, and it started when I went to ICTS to give the same talk, this is Ashok's suggestion. Take string field theory, take the first massive level, derive the Lagrangian from string field theory and show this is the propagator. If that's a propagator that comes from general gauge fixing of the string field theory action, okay, maybe there is something sensible going on. Okay, thank you.
One, I thought it was just statement that if you have high enough energies, then everything should go over to relativistic things. So
No, the 3-point function. The nature of the 3-point function will be dictated by the 3-point function of the unbroken theory. It's not that the structure, also the 3-point function structure knows about it is actually going to the unbroken phase.
Let me ask once more about your propagator. So your propagator, does it have a pole that is the index structure of the, if we look at the pole part, is it only for this projected for the right representation or not?
It is projected for the right representation only for z equal to infinity.
Otherwise, even the pole part has.
Thank you. So, okay, there is an ambiguity whether you take the on-shell limit first or c equal to 1 limit first.
Let me stick to fix xi.
Fix xi are not equal to 1.
Yeah.
Then you are right that the residue at the pole is always correct.
Is correct meaning?
It's correct means it's the correct. It gives the residue at the physical pole gives the correct residue in terms of the polarization.
That's only the right.
Correct.
State.
Correct.
And were you working at? You were working. Okay. Now, if you were working first at z equals 1.
Z equal to 1, then you see it doesn't give the project because you see this drops out, so it becomes a theta mu.
So even on shell you have.
There is ambiguity about this equal to 1 limit and on shell limit.
Yes, this is the problem. I mean, had it been that you were then at any other xi,
yes,
then you would not have had this problem, right?
It is, but point is that then it has other unphysical poles, which I cannot cure it. If my amplitude has other poles, then the residue should have some physical meaning, right?
Sorry, this xi I'm not so familiar with, but were we using a propagator such that if we sit on the pole, the residue is only of the correct representation?
Okay, let's take this discussion for an explicit case. So let's say W bosons, okay? So then let's say I have eta mu nu, p mu over p square. And then you have some 1 over p square plus m square minus I epsilon. So when you take the limit, when this is the on shell, p square plus m square equal to 0, It has the right property, no problem. But it has unphysical pole at 1 over p square. But in Higgs mechanism, the unphysical pole is cancelled because there is a would-be boson whose contribution comes exactly opposite of it and cancels. Right? And that is true for any xi. In that case, if you have some xi m square, it always cancels for any xi. It always cancels that unphysical pole contribution from the unphysical pole. We could not make that argument work for our higher spins.
And then xi is equal to 1, you couldn't have double pole.
No.
That's why you had xi minus 1.
Correct.
To
Correct.
remove that.
Correct. It's this point that whether you're taking xi equal to 1 first or on shell first. If you're taking xi equal to 1 first, all poles are all physical poles, but the residue is a problem. And the residual problem, precisely what Siraj was saying, the trace, double trace, triple trace, those are the residue problems. So remove it by adding these ghosts, would-be Goldstone bosons. Sorry?
So I think we need more than Goldstone scale also.
Yeah. I am calling all of them whatever. I mean, at this point, it's just an observation, right? You need everything. That's what I was saying. You need the full tower. The tower is not just scalar, it's a whole tower from S minus. No, it's a whole tower that is needed.
But the tower of would-be particles.
Would-be particles, yeah. And that works as a representation theory because of the arguments here. Correct. But I could not. Point was, I was hoping that when I add them, I can make it psi independent, just like I can show it in this case. So now the hope is that let's do it for all general 3-point function, which is just, you understand, computationally very taxing. But let's see, I don't know. Only thing I can show you, which we checked it for spin 2 and spin 3, we checked whether loop is good for c equal to 1. And it works for c equal to 1. It doesn't work for c equal to infinity.
So this is what you've been saying. But suppose I made the propagate intermediate minus PU by m. Then that has no problem.
That has no problems.
That's your xi equal to infinity.
That equals xi equal to infinity. And that is precisely the complete set of state summation.
Right. So if you were right. Okay, I get it. And
yeah. That's the on-shell thing, so that works. So that's we have given in the appendix. So that c equal to infinity, we have a proof. But other values, we need a Lagrangian. We don't have it.
But for your purposes, this is the would anything go wrong if I just use that property?
Tree level, no. Loop, it seems that c equal to 1 is better.
To get this diagram, like iconal diagram.
I need the loops.
Yes, you need the loop, but there is a prescription that you take the tree-level diagram and you do Fourier transform.
Correct. That prescription, so Suman, what you are saying, I think the prescription basically predicts the discontinuity at the cut, which is basically like looking at like the analog of taking the residue at the pole.
Yeah.
But what about the optional contribution? What about general thing?
You're saying that prescription doesn't.
That doesn't take it. It only takes care of the imaginary part of the amplitude. It doesn't take care of the real part. And real part will be sensitive to all these things, maybe genuine 4-point contact terms also. Right? If you want to do something like CRG, then not just these contact terms needed to do gauge invariance, but also genuine gauge invariant 4-point contact terms. We have not classified them. Because in string theory, those are there, right?
No, I agree about that 4-point contact term, but just to get this ladder diagram, I thought that's an exact proof that
ladder, not the ladder diagram, but basically the discontinuity of the ladder diagram, there is a proof. But if you are interested in, let's say, the ladder diagram, the full thing, then I don't think there is a thing. Okay, so in that sense, one can go ask this thing. Another way to quantify this thing could be to go in higher point and fix the 4-point contact. We need some sort of an algorithm to make sure that if S point works, S plus 1 point works, and if L loop works, L plus 1 loop works. Then at least this will be a correct perturbative rules. Then we need a derivation. But that will not give you the pole, typically, unless there is some sort of confinement or something. These are elementary particles, so that the 2-point function has poles, no branch cuts. Any other question? No, the exchange diagrams are high spins, right? Yeah, this is the exchange. So in that sense, gauge invariance now is in control because of the reason I said you. All other 3-point functions are optional gauge invariant. So once you declare victory for this, you declare victory for all 3 points for gauge invariance is concerned. But explicit expression and taking them, and that is still missing.
So here it's the loops that is your main motivation.
Yeah, I would like to show that loop works. So if you ask me, I would like to show the loop works, and also to understand this point which people are saying that there is some points where the UV growth becomes better. What does this statement mean? Can I actually compute the amplitude and the whole space and show that there is some special points? Or another question one could ask is that in this 3-point functions, where does the string theory lie? What is the linear combination string theory predicts? Is that a special point?
But will this improvement in the loop calculation help in getting the uniqueness of the tree-level string amplitude?
I don't know. That will need a lot of work, because actually you have to now add a tower, and then you have to get you have to resum the whole tower and get a contribution. I don't know how to do that. Right?
In issue when you add a new principle.
No, I'm saying, will any loop level information help say something about the tree?
Yeah, but maybe there are
That needs more in principle, because you are saying that CRG is tree level dependent principle.
CRG is a one principle, but maybe there's some new principle that.
Correct.
So another question one can ask is that if you add this and compute all the beta function for, let's say, mass for the light particle,
Exactly.
does the beta function become special at some point of these things? Because not only in that case to show string theory, I have to show the 3-point functions are fine. I also have to relate the mass to the spin, which I am clueless actually. Or to do this computation in first string field theory for, let's say, first 10 levels and see what it is saying, and then take that thing and mimic it here. That's a good part. But after this last review of Ashok and Zuibak, all are explicitly spelled out. So I say that the Weinberg for string field theory is written. Now one has to do something like a Peskin and compute everything. And yeah.